Hey everybody. Welcome to the second week of lecture, the third week of class, maybe depending how you're counting. So by now you should have done assignment 1. Hopefully that's all gone well. I'm of course recording this in the past, so probably. And assignment 2 coming up this week. So let's have a look, shall we? Well, lecture-wise, we're finishing off these Hadoop concepts today, which is good because we're finishing off Hadoop this week in assignments. Assignment 2 starts the transition into Spark. So again, I think we've really seen MapReduce here as it's an interesting chance to see how these things work and how all the gears turn. Spark is a way to actually get a little more done. And as you can see, I am, as promised, filling in this schedule here. And I didn't do this before the first lecture, I forgot, but I will fill in the length of the video. So like, I know when you see if you're watching this as a premiere, you don't really know how long it's going to go on. I will fill that in here. And if there's 2 videos, of course, I'll put both, just so you know what you're in for. You can plan your day. Okay, so we were here talking about MapReduce and this word count code. Here are some of those classes that are moving around and doing stuff for us. Because again, I think a lot of that it's there in Hadoop. Or in MapReduce, I should say. You might not notice, like if you just kind of work with this template code that you've been given, there's a lot of stuff here. You might not notice these details, like what's that doing? What that's doing is it's an input format. So that map and reduce that I right away said it's actually map and shuffle and reduce. And then I said, oh wait, it's actually map combiner. Those are kind of combined, like they're in the same process, but mapper, combiner, shuffle, reduce. I have something to put on either end of that story, which is first you need the input to the mapper. Like before you get anywhere, you need to decide, well, what is the data the mapper is going to get? And that is what an input format does. So wherever the data comes from, and in the docs here, input formats do whatever it is they do. Mostly they get a collection of chunked up input, but where do they get it from? Well, it depends on the class. I do like the Java docs here. Here are the subclasses we know about. This one itself, as far as I know, is it's a class. I don't know if Java has the concept of an abstract class or not, but again, you can see there's type arguments. These are the key value pairs that it produces, right? So it gets its input from who knows where. It produces key value pairs. So we're working with files, and specifically our the word count, and in fact the Reddit as well, were both text input formats. So we had this. They produce key value pairs that were long writable in text, and there is something I said in the last lecture. The key is the position within that file, and the value is the line. We've never needed the position in the file, but it was there if we wanted it. If I wanted a different key or a different value, I want a different input format. If I want, I don't know, the file name or something, I could do that. I would need to probably override or subclass or something myself and start writing some code, which is not the end of the world, but would take a little work. So there's other stuff here. If you're reading the key value like file format, I think this is it's a format from some application. I don't remember which one. Or you have like data that is in fixed length fields. So, the first 100 bytes is record 1, the next 100 bytes is record 0. And in that case, you would get a long writable that's probably, again, the offset in the file, and then the bytes, right? You said I want 100 bytes as each record. And of course, there's some way to say that number, how many bytes. And in the text input format, what we saw in that code was we got to say, read these files. So, you're going to read some text files for me, break them up into lines, because that's what text input format does. We had to tell it which file or which directory of files, I guess. So we took that from the command line, but that's why that worked. know what? I should have another. So I'm going to reopen this so I can keep both tabs open. Okay, the mapper process we've talked about. You've written one. But again, this is input key values, output key values. There's, of course, docs here for what you have to do. But fundamentally, what you have to do is override the map method so that as the input format that you've chosen produces key value pairs, for every one, this function gets called. You take it, you do whatever it is you want with it, which probably is going to include some context.write, which is the mapper output, which gets passed along to the next step. And of course, in our overall job here, so we created this job and we said, okay, this input format, this mapper class, and this combiner and reducer. So again, like I said, the combiner goes with the mapper. And in fact, it's part of the same process. So it's not like you run a mapper and then you run a combiner. It's you run a mapper process that takes one of the input chunks, deals with all of it, and does the combiner work all in that one Java process. I guess something I didn't say there is split it up. So one of the jobs, again, of the input format is to sort of take this thing and split it into chunks. All the file input formats, I think, are file by file. So it's one file becomes one chunk of input and therefore one mapper process. So when you ran this, and I think you would have seen this in assignment 1, if you have 10 input files, you end up with 10 mapper processes, each one reading from a file. There's a little footnote on that. If the files are really big, it might get split, but mostly one file becomes one map process. So, and that means if you sort of have insufficient parallelism, right? If you have individual files that are huge, well, maybe you're going to find the single mapper process takes too long. Maybe you should just split your files. Like that is probably the easier way to do that if you want a different number of mappers. Again, as we go through the story here, mapper combiner, and then the shuffle. Again, we don't get much control over the shuffle. The thing that is controlling it is this partitioner class. And this is, as the mapper / combiner output key value pairs, how do we decide which reducer it goes to? Basically, how do we do the shuffle? So that's the partitioner's job. And I'm sure it says that here somewhere. Yeah, how do you partition map outputs to reducers? Which one of the reduce tasks gets that key? And the default there's other options. The default is hash partitioner. That is just take the key, calculate its hash value, mod the number of reducers. So if I have 5 reducers, calculate the hash value. That's an integer. Mod 5. Send this key to that reducer. Which is what this one method does. So that seems fine. If you really want to differently arrange your shuffle, you could have overridden that partitioner class. And then the thing you actually have to do, the thing you're thinking about, the reducer, which is, again, you've seen this. This is fundamentally the reduce method that you override as a programmer. For each key, this gets all of the values that were with it. So when the mapper or combiner produce key value pairs, this specific key, all of the values, give them to me and do something. Once again, so we saw like long sum reducer. There's one for us that's built in. We could have used it. We did use it. Same is true for the mapper. There's a few here, I think. I don't know, like whatever these are. If you need specifically to do some regular expression extraction, there's a built-in thing for that. I guess they decided that was a common enough use case that you should be allowed to sort of just import it rather than write it yourself. But of course, you can write your own. Often it's only a few lines of code. And then I guess we saw this too, right? The combiner is fundamentally a reducer that's kind of running in a different spot. It's running over in the map process, not after the shuffle on its own. And then the output format, where again, we saw this, whether you noticed it or not. we said text output format. And again, this is why we got, for each reducer, we produced a single file, and the file consisted of lines that were key tab value new line. And that was the text output format. And I'm sure in here somewhere it says all that. Oh, look, I can change. Like if I want something other than a tab, could have changed that. And there are defaults for all of these, which I didn't do. And in fact, if you just find the word code example on the Hadoop website, I think they don't set the input format class because you don't have to. This is the default. This line doesn't actually do anything. It changes the input format from text input format to text input format. Same for the output format. The default is text, but we include it in this code just to be a little more explicit. It turns out there's actually a default mapper as well. The default mapper is when you get a key value, context.write that key value. Just copy the input to the output. And there's a default combiner that's exactly that. Every record you get, just copy it. And there's a default reducer. It's the exact same thing. So it turns out if you don't specify like any of these things, you just get a MapReduce job that basically copies input to output, which is not very exciting, but it'll work. It'll do something. And again, I guess the other thing we had to set there, just because Java is fuzzy with these types, we had to set a few more. But that's what's going on in there. And again, I think you saw this in assignment 1. This is the sort of summary output that's produced from a MapReduce job. So a bunch of other stuff happens there as things are going on. But this is what I got with this specific input set and with 3 reducers. Oh, and by the way, actually, you know what? Since I see it here, this command line argument, the -d something something, in my main function here, the tool runner is what's taking care of that. So the fact that I can say -d numReduces equals 3, this tool runner, its job is to, take the command line arguments that actually got given and build these configuration objects out of them. Pass it off, and then this configuration sort of works its way in here. So that's why that command line thing worked. It's that tool runner and this configuration object that gets moved around in our code. But yeah, so when you run this, there's this kind of nice summary of what's gone on that maybe it's just interesting trivia, but sometimes it's like really useful debugging. Like if something has gone wrong, sometimes you can see it here. So, I read 92 million by 92 megabytes. Sure. I wrote some amount. Okay, this is probably a little more interesting, right? So my mappers, so all the mappers together received 257,000 records, lines, right? So I had that many lines of code, or lines of text in my input. The mapper produced 2 million and a bit output records. So like on average, each line had 10 or so words. Yeah, that makes sense, right? If I saw these two numbers being exactly the same, that'd be really suspicious. Like I don't think the average number of words on a line is 1. If it's 9 or 10 or whatever this is, that seems about right. And then my 2,136,000 mapper outputs became 2,136,000 combiner inputs. Yep, that makes sense. Those two numbers should be the same. And now we can see like this is what the combiner did. And if you shut it off, these two numbers will be the same because again, the default combiner is just a copy effectively. But this was, I had my mapper produced 2 million and some records. My combiner managed to chop that down to 240,000. So I saved, what is that? 8 times one. I only used 1/8 of the network traffic for the shuffle that I would have otherwise, like whatever the ratio is there. I saved a bunch of network traffic with my combiner, and I can see it there. So yeah, that many output records from the combiner became that many input records to the reducer. Those should be the same. I had, so of 242,000 records, I had 124,000 unique words. That's kind of more unique words than I would have expected, but well, again, we're counting things like numbers and like that kind of like 12th as words. So maybe if you have these things that I might not consider a word, but our regular expression does, 124,000 sounds plausible. So I had that many unique words. I produced that many lines of output. This doesn't have to be true, but it is from my code. So in this code, the reducer for each key calls context.write exactly once. I could have done something different, but for this logic, that makes sense. So yeah, each unique word gets one output record. So yeah, in this code, I expect those two numbers to be the same. So I had 57 map processes. So I had 57 input files, I guess. So again, each input file went to one mapper. Do I not see, where's the number 3? I would expect to see 3 here representing the number of reduced processes here because I did that. Anyway, so yeah, that's at least a quick tour of what happened there, how we got those. And again, maybe that was useful debugging information. Maybe it would have been really useful if I'd done something wrong to notice, like, wait a minute, these two numbers are different. Why is that? Or even like, oh, if I see my output is empty and I see a 0 there, well, it's not a file system problem. It's my code problem. I have to kind of work back and find out why. So it can be like, and I understand that it's like, it is hard to debug these things because they're big and parallel, and the code that throws the exception is actually running over there on some other computer. Yeah, that can be a pain. You know, sometimes you have to read these little hints that you're given very carefully to figure out what's going on. All right, so let's not forget the goal here, right? Like the goal is to do a bunch of stuff concurrently, because I have, again, either like you can run this on your computer, and you probably did when you were testing, and I certainly do, you know, on this computer when I'm testing. So I've got some number of cores, 6, 12, depending how you count. I want to use them. And this is something where I think most programmers, for most of the programs they write, don't, right? They write single-threaded code, and one thing happens after the other, and you use one core. Most of the time, that's fine. If performance isn't an issue and you're not doing a lot of compute work, whatever, great. Here, we want to use all of the processor cores on our one computer or all the processor cores on our compute cluster as much as we can to get the job done. So like I said, the input format is in charge of breaking up the input and thus effectively deciding how many map processes I'll get. On the cluster, at least, Yarn runs them. On your computer, they're just processes, and your operating system runs them. Again, there's this question of data locality. Yarn knows I need a mapper process, but it also knows I need a mapper process that's going to read this file. Please try to put it on a node where that file can be found locally in the HDFS. Maybe Yarn will come back and say no, but it will try. Like I said, the text input format is one file to one mapper, unless it's really big. There is this concept of being splittable. An uncompressed file, like the thing is, like if you have a gzip input file, you can't just start halfway through a gzip compressed file, or most compression algorithms. You have to start at the beginning and read the entire thing. So you can't, even if it's a 100 gigabyte file, you can't just have two processes read it really in parallel. You have to kind of go through it sequentially. Took me a while to figure out why that was happening one time. So again, like the way we've arranged the universe, mappers are independent, right? So a mapper gets input from a file or whatever the input format is, and it can just do its thing, produce key value pairs, run the combiner that goes with it, and for word count at least, get these like partial results. I want that to be kind of big enough. And this is going to be a theme in the course and in general of any kind of like concurrency, parallelism in code. You need like the right number of tasks, and the right number is like It's not 1, and it's also not 1,000,000. Like somewhere in between, like I want all my CPU cores to run. I probably want, like, even if I have one mapper that's like really efficient, I don't want, like, if I have 10 processor cores, I don't want exactly 10 mappers, probably. I want like 20 or 30, so that again, if one finishes quickly, one is a little bit slow, the scheduler can kind of balance all that out. Again, if I have 10,000 input files, I start to hit overhead, which is just, there is a little expense to start up a mapper, do the thing, shut the mapper down. I'm okay, fine, I can do that 100 times. I don't want to do that 100,000 times. Again, this is always the case whenever I talk to anybody about concurrency or use concurrency. It's, well, you've got to pay attention to how much concurrency you're getting. You don't want too little, you don't want too much. And here it's determined by our input. How many files did we have in that directory? If you're unhappy with that, there's a couple ways around it. Well, you could write a whole new input format that does something more clever. You could change the input files. And let me tell you, I want you to think, well, let's see, I could figure out how to write an input format in Java and figure out where to put it and compile it and whatever. Or I could just make my files different. So like this link is to the Unix split command, which is, you say, well, here's an input file, break it into chunks that are this many lines long or this many bytes long or whatever, and then put that in HDFS. 100% of the time I would do this. Get your input in shape, deal with that sort of first step of concurrency that way. It's going to be the same advice in Spark as well. Like we saw in assignment 1, and like I said a few minutes ago, we got to decide how many reducers, because MapReduce can't guess. So it can guess the number of mappers because it has the input format telling it. It's like, look, I have this many files, so I can give that to this many mappers, and we didn't have to worry about it. Maybe we did, maybe we should, like maybe there's a situation where it's wrong, but it'll take care of itself most of the time. The number of reducers we had to pick, again, it's a question of how much concurrency do we get. You know, I'm the only one as a programmer that knows how many unique keys I've got. Is 124,000 a reasonable number to give to one reducer? Yeah, it's fine. That's a small number in modern computing. So yeah, one reduce process can iterate through 124,000 records and it'll be okay. Or I can say, well, nah, you know what? I think it's going to take a long time, or my reducer does some really like computationally complex thing. I need 10 reducers. So that's, again, like the compiler or the MapReduce framework doesn't know what I'm about to do. It doesn't know how complex it is or how many keys are about to be produced. Hopefully I do as a programmer. So that's why that one's my choice. And the reason we got these multiple output files is, again, it's the concurrency coming back to show itself. I want each reducer to work independently. I don't want the reducers to have to coordinate and say, well, I'm going to produce one output file, so reducer 1 is allowed to write, and reducer 2 has to wait. When reducer 1 is done, then reducer 2 can start. No, this is crazy. I want all of them to work on their own, not coordinate with each other. So each one produces its own file. I, again, as a user, think, oh, look, I have 4 output files, but that's okay. I'll just think of them as one output collection. Another, again, footnote that I just mentioned last week, I thought maybe be explicit in the notes here. This writable thing, this like writable interface, where we did things like, int writable, say, or long writable, then we switch to. These are basically wrapper types. So it's, this one fundamentally is a class that holds a long, but it holds it in such a way that Hadoop can serialize it and deserialize it. So really what matters here is the like write and is it a constructor to read? Read fields. Yeah. So it's write and read fields. That's take take the object and turn it into bytes, and take the bytes and turn it back into the object. These have to be fast and deal with whatever this data input class is. So that's what this writable class is all about. It's MapReduce has to be able to take whatever I give it, ship it over the network quickly, and reconstruct it on some other node. So I don't know, like, I guess I can do that with an array with some footnote on it, probably. That's what those are doing there. There's writable comparable, which I need for the shuffle, because the shuffle has to be able to decide, again, like ask this question about what node something goes to. So that's what these were doing. I really wish that the text class had been called string writable, but again, nobody gave me a vote on that one, because everything else is type writable. This one is text, not string writable. But it is, in my mind, it is. So in, I guess I probably should say assignment 2, but that's what, again, this long pair writable, this is not complex work. You know, there's a few actual real lines of code here, but not many. But this is, I want to represent 2 long values instead of just 1, because that's the value that I need in that context. No, I guess this is assignment 1. Okay, again, this is not advanced work. However you read a long, do it twice. However you write a long, do it twice. That's all this code is doing. But I had to do that to satisfy MapReduce, because that's the type of thing I wanted to pass around. I think I can probably let this go. Yeah, like, this is, again, what was happening in word count. I think I was, like, I think I covered this with a lot of explicitness last week. But this is what's going on here. With, again, a little bit more data-centric, I guess, approach to it. Text input format says 241 bytes into the file. I found this line. Mapper breaks it up. Combiner does some partial summations, whatever it's seen. Of course, like, this combiner doesn't know what the next mapper over is counting. So the next mapper over probably has this, you know, some more copies of the word line. The shuffle happens, and then the reducer is in charge of getting all of those together and doing the final work. And the output format gives us a text file. So MapReduce is cool, right? Like, I get a lot of concurrency happening. Like, the map and the reduce tasks both can be done in parallel. It's sort of as many cores and input files and stuff as I have. The shuffle does take some work. We haven't, but we can take multiple, like, do this MapReduce, take that output, read it into the next step. So MapReduce, 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 a bunch of tasks all stitched together to make a job. At some point, it does feel like we're pretty limited here in what we can do. Again, a more like type-centric approach, I guess, to what MapReduce is doing, if this feels good to you. The input format takes whatever input it is and produces some key value pairs. Again, I might have an empty file. I might produce 0 from one file, but, you know, in general, some key value pairs. The mapper has to take that key value type as input and produce some more key value pairs. Again, maybe 0, maybe 1,000,000, I don't know. The shuffle's job is to look at these keys and get them together using whatever comparison thing. The reducer gets, again, these keys, and we saw, by the way, we did see a little bit of a type change. The mapper, combiner, and reducer, but can fiddle with types a little bit. But I guess the combiner fundamentally has to take this and produce this. So if I have a combiner, it has to take in and out the same type. The reducer gets one key and a collection of values. Maybe list isn't the right word there, but collection of values, and produce, again, some number. Word count produced 1 for each key. We produced 1 key value pair, but it could be anything. And the output format takes those and does something with them. Write them to a text file in our case. Another, again, look at this that you're asked for in assignment 2. The how many the view counts in Wikipedia, I guess. So again, here we have multiple files, and I guess in this one, the extra little trickery that's happening is we need to know the file name. The file name actually contains effectively a field that we care about. What date and hour did this happen on? It's not in the file, it's in the file name. So we had to peer into the sort of metadata in that in the mapper to retrieve that piece of information. What we got out of the input format was, again, position in the file, don't care, line of text, that we care about. And we asked some questions about it, and we disassembled this by splitting up around where the spaces are, got this out of the file name, and the mapper produced, well, will produce, I guess, I should get, again, the verb tense right. On this hour, I guess, 20 is the value I saw. And then I saw on this hour a 2 and in this hour a 1, right? So we break those up and we have a string and a number. We could have not had a combiner, but we do. So we have a combiner here that's going to take all of these things and for each hour find the max value, because fundamentally we're finding max here, and we know we can do that kind of partial calculation. I guess what I've drawn here is I'm imagining if this was some huge file, if the input format knew how to break it up, it could give the first half to one mapper and the second half to another mapper. Again, our input files aren't that big. In reality, I don't think a gzip file can get this treatment, but in theory, it might happen, right? We might have more mappers here than we did have input files. Again, so the combiner does its thing. In this case, we're using the same reducer for both, and it's for each key, take the max or find the max value and do that, right? So iterate through these, find the max. This is, again, good first year programming, and then output the one true maximum for each key. Each reducer produces a file. Again, as I've drawn the picture, I've got 2 reducers. Maybe I need 1. In fact, I guess, given that the key here is hour, and it's something about Wikipedia, the number of hours Wikipedia has existed is not a big enough number that I probably need 2 reducers here. So I can probably bound this and say, you know what, for this problem, 1 reducer is going to be just fine, but I've drawn it as 2. So again, that's what's going on with MapReduce. And we move on. So again, I think MapReduce, again, in my mind, it's a good teaching tool. It's a good chance to look at what's actually happening and think about what's actually happening on the cluster in order to get this work done. It's maybe not the most practical way to actually analyze data. Spark being a much, much nicer tool. So I'm going to assume that you've written some Python, that you're not a complete Python noob. And we're going to be working with Spark in Python, even though there are other programming language choices for Spark. I think Python is probably the most common in the data world. And of course, just a nice language to work with. So what I want to talk about here are a few things that I think even if you're sort of a normal Python programmer, you might not have noticed in the language that are worth bringing up. So it's a nice language to work with. I think most people who have worked with it will agree with me on that one. It's pretty common for data science. It's by far the language of choice for data science, unless you're trained as a statistician, in which case it's maybe R. We're using Python 3, not Python 2, just to get that out there. It seems like a weird choice. If you're going to work with, terabytes of data or whatever, even gigabytes of data, Python doesn't seem like the right choice. It's not generally that fast. It's compiled. You don't see it explicitly, but this is just a hot button for me. People who say like, oh, Java's fast because it's compiled, Python's slow because it isn't. This is a false statement. Python's compiled. You just don't explicitly do it. Python's not slow because it's not compiled. It's slow because dynamic dispatch, but that's another course. So I like it. There's this Zen of Python document, which is sort of a philosophy guide, I guess, for the project, and it speaks to me. Write beautiful code where you can. It's nice to be explicit in your code. If you've ever written Ruby on Rails and had that convention over configuration, this is the opposite of that. It's there shouldn't be magic. You should have to say, like, here's what's going on. I feel this one very much. I often have students ask me, like, oh, should I put comments on my code? And my first answer to that is, your code shouldn't need comments. I feel like sometimes you have to comment code, but when I do it, it's like, step one, admit that I can't make this implementation so simple and beautiful that it can be read without comments. And if I really can't, if there's some trickery that has to happen, then leave a comment to say what that trick is. But simple is better than complex. And again, I stand by that. Data types in Python, and the basic things you'd think. Python doesn't have static typing, so variables don't have an explicit type. Values have a type, but when you write code, there's no types declared on anything, and if whatever value you put in that variable will be held by that variable, and as long as you don't do anything that isn't allowed on that type, it'll work. Again, a couple notes there. In Python 3, this is not true in Python 2. Strings are Unicode strings. So this is exactly as good a string as any other. It just doesn't happen to be ASCII text. That's fine. Text and bytes are different. So if the term, like, okay, here's my pop quiz. Do you know the difference between a character set and a character encoding? And experience tells me probably not, even with an example on the screen right now. The short answer is Unicode is a character set. ASCII is a character set. And that is a collection of characters. Capital letter A is a character, lowercase a is a character. And they're numbered. So uppercase A is 65, lowercase a is 97. That's a character set. A character encoding is, how do I turn characters into bytes and bytes back into characters? So with ASCII, you didn't really worry about it. You said, well, 1 byte, 1 character, and you put the number in the byte. For Unicode with 170,000 or something characters, we have a few more options. I'm going to stop the explanation there and just say there's only one character encoding I care about, and it's UTF-8. That's how text gets encoded. Don't make your life more difficult. So this, by the way, in Python, so this is a string. S is a string. B is a collection of bytes. So again, string is a collection of characters. This is a collection of bytes. These are 8-bit bytes, like you can send over the network or put on a disk or whatever. Encoding and decoding characters is the process to interchange between those, and you need to know which character encoding to do that correctly. UTF-8 is going to be the default choice for everything because it's the modern world, and it is the default choice for everything. Anyway. There's two sort of immediately obvious collection data types in Python, lists and tuples. Conceptually, they're not so different. A list is mutable, a tuple is immutable, but by convention, lists are like, lists are probably going to always hold the same thing. So I'll have a list of strings or a list of integers, even though it's legal to have a list with a mixed collection of data in Python. Tuples are, again, conventionally sort of like an ad hoc data structure. So, I might have a pair like this that holds 2 floats. I'm going to think of those as a latitude and longitude, and then I have a list that's a collection of those. Again, there's no rule that says that's how you have to use Python, but by convention, it's probably the thing you should do. I will, by the way, I think I'm going to say enough today. I will take a break. So in, I don't know, 10 minutes or so, I'll take a break. There'll be a second video that we'll pick up after that. We'll continue from there, but not yet. So, dictionaries in Python are, again, like, probably one of those terms, even if you've never done it in Python, one of those terms has probably come across your view in some programming language. It's this key value lookup data structure. Again, comes up reasonably often, probably not as often as like tuples in the world we're about to enter, but they're a handy data structure to have around and built in, which is nice. This is going to come up with Spark RDDs, where we're going to start. And I don't know if I can, there we go. So if you have a pair, either in a variable like this, or maybe it's passed in as an argument, or it's returned by a function or something like that. So it's pretty common to have a function return two values as a pair. So in your function, you would say that, and then as you get it back, you would say that. I guess here, I'll match my slides. So that is, again, if I have a pair, I can do this unpacking assignment. So I have to have the same number of things here as I have here. If I do something like that, no. And you can even do this. If you do have a sort of more deeply nested collection of pairs, you can unpack multiple nested levels. And again, like with Spark and RDDs, we are occasionally going to have these collections of things because sometimes we need key value pairs. So this, like val, is a key value pair. It has a key and a value. Sometimes with Spark and RDDs, we're going to need that. So we're going to have these sort of unusual pairs sometimes that are three values, but we have to structure them this way because they have to be key value pairs. I'm a little sad to have lost this. In Python 2, you could unpack in the like argument signature of a function, and now you can't. I guess I was the only one that used it and liked it. But in Python 3, you have to take the argument and then unpack it as this multiple assignment statement, sort of a line later. You know, so be it. Again, apparently I was the only one. One thing that, again, I guess depending on the programming experience you have, if you spent your life, especially in like C and Java, this is going to moderately new style of programming. If you're a JavaScript programmer, this is old news. But in Python, functions are just values. Like in the way that 6 is a value, the function double here is a value. It has a name. Well, I guess the variable, like if I say x equals 6, x is a value. I probably shouldn't call it double. No, double's not built in. So again, double is a value, x is a value. I can assign things. That thing, all of those things kind of work. I can also pass a function as an argument to another function. So this, whatever it's doing, doesn't really matter. But so double of 10 is 20. Double 20 is 40. Yeah. So I can do this, and I can do this on basically any function I want will kind of fit in here, as long as it kind of, returns an argument that can be passed into itself in the second step there. We're going to be doing this a lot, like passing around functions as arguments to other functions. Again, if you haven't seen this in another language, please be advised. It works in Python and is pretty common here. In fact, we're going to be using it like this. So I guess this is the first, like, arguably little bit of Spark code we see, because we're going to have a data type, and we're going to map. So this is going to be for everything in this collection of values, apply this function, put the result in this variable. That's why this function is, or this first class functions comes up here. It's because basically what we're doing here is we're passing around a little piece of logic. So Spark needs to do something to every value in our possibly huge data collection. What it's going to do is described by this function. That's why we need to do it, because we need to basically say, please do this, again, in parallel across a computing cluster, and this is how Spark is going to let us express it. At least the first way Spark is going to let us express it. And this is one, you know what, this is I'm going to say this is a failure of a lot of Spark documentation. This is, I mean, again, like if you have ever written any Python at all, this doesn't look like much of a surprise, right? Define these functions. And in fact, this might look pretty familiar, right? Like taking a word and turning it into a pair, word comma one, that's something we've done before. Whoops, there we go. And again, perfectly reasonable. Like there's nothing wrong with this code I'm writing. But what you will see written quite often, especially in Spark tutorials, because you end up with these functions that are so short, right? Like this is not an appreciable amount of logic. You will see a lot of Spark tutorials, and for good reason. Like you save yourself a few keystrokes once in a while and write it as a Lambda function. So that's an anonymous function in JavaScript or a Lambda function in some other languages. Where else do you see this? Ruby programmers write these blocks that are effectively anonymous functions, basically function that doesn't have a name. In Python, there's a little limitation on that, which is I only get one expression. I can't write big complicated logic. I only get to write a single expression. So, yeah. What do I want to do here? Let's do, just so I can do an example, pardon me. This is a slightly weird thing to do, but it's okay. So, again, I'm going to have, this is going to get passed in as F here, and I'm going to do it twice. Why do I want to do that? I don't know, because I do. I just decided. So take the thing, pair it with one, and then just the way this function works, it's take that and again, pair it with one, call the function twice. It's a weird bit of output, but the thing that ends up happening in Spark is you do this kind of thing so much, and with these really simple bits of logic that, well, this is a way to say, take one argument, call W, and return W comma 1. It's exactly what this thing does. I just didn't give it a name. I can do that. And I guess I should actually show you. It does the right thing. I will ask you, okay, everybody raised their hand. Which one of these is more beautiful and more readable code? And I think, okay, even though this version took a few more keystrokes, I think it's this one. I think this is a lot easier to read because I have this like free documentation of a function name. Yeah, that being said, this is simple enough that, yeah, I guess I could figure out that one pretty easily. You'll see a lot of Spark tutorials writing a lot of Lambda functions because they're just, again, they're shorter. You can fit them on a slide more easily. Often the logic in the tutorial is very simple, so they do it. I don't think you should all the time. And in this case, this add operation that I happen to be using in the slides, it turns out there's a built-in, and I didn't even have to write it. But so don't do this. Like, I think honestly, if you have to take, like if I have to give one word of advice on using Lambda functions, it's don't. If I get to give a few more words, it's usually don't. Yeah, I can give all of my advice on Lambda functions in 2 words. Usually, no. Please don't do this. Nothing makes my eyes hurt more than this. Because you know what this is? Again, the Lambda function takes x and returns f of x as a result. I already have a function that takes one argument and returns f of x as a result. It's f. Don't write this. I hate this so much. This is one that will cause me to okay, I won't really. I shouldn't say this, but I'll think about just disconnecting you from the Zoom call, just banning you from the chat. Don't write a pointless Lambda function around code for no reason. Anyway, you think about that, because I'm going to take a break here. Whatever time it is, in like 9 minutes or so, because I see I'm at 51 minutes. So the next chunk of the lecture will be in a separate video. It'll be linked from the course notes, or it's probably a suggested video because it'll be in the same playlist. But yeah, 9 minutes or so from now, I'll pick up, do another chunk of lecture, and we'll carry on with some Spark. See you in a little bit.